Well, welcome to this video. In this video, I will be discussing regarding the Bell inequalities. So, in the few videos that will follow this, so there will be 3 to 4 videos, and I will over the 4 videos I will be completing this discussion as it was not possible to sum it up in one video. So we start with the understanding and building up the necessity that we will require to understand the Bell inequalities in hidden variable theory, as well as what is the quantum mechanical counterpart. So the first video will be just an introduction. So let's see. So the Bell inequalities are mainly has its root. It mainly follows back to the argument of Einstein, Podolsky, and Rosen, the EPR paradox, and what these three they believed that quantum mechanics was incomplete. It was an incomplete description of nature. Particularly, they didn't like the fact that these superpositions and this probabilistic theory that lies in the heart of quantum mechanics, they were very much not satisfied with that. They felt that it's like the God is playing dice, as Einstein has said that. So their claim, the claim by these three person, it was that of local realism. So to understand it intuitively, locality means that whatever experiment we do here should not affect experiments that someone else is doing someplace else. And the understanding of realism, we will see what exactly this means. The understanding of realism is the fact that the property of the particle is an objective reality. Suppose you see an electron and it has this spin, and quantum mechanics says that it is probabilistic, but in reality, as it is a objective feature of the particle, the spin of the particle must be predetermined. These all things is what EPR believed to be true, and they were quite logical and quite reasonable. And quantum mechanics was not able to convince about the truth of these arguments, particularly the entanglement theory. And further, Bell transformed these vague understandings of reality and locality into what we call Bell inequalities. And then it provided the experimentalist with a handle on checking whether quantum mechanics was true or EPR claim was true. And finally, it was found that indeed quantum mechanics was true. And local realism is not something that nature follows or abides. So to understand this throughout my video series, I will be following the work of the original work of Bell, and so it will be just again retracing those steps. So we start a bit with understanding of the entanglement. So given a system, suppose we have a two-particle system, the joint description of the system belongs to a Hilbert space H1 tensor H2 as per quantum mechanics formalism. And if a state belonging to this larger Hilbert space can be factorized into these states that belongs to the their own Hilbert space associated with particle 1 or particle 2, then we say that this state is not entangled. Else, if it can't be written, then we say that psi is entangled. Actually, in terms of density matrix, we say that what is called correlations. The point is that given a density matrix of an entire system, so this is the representation rho AB for the entire system, we can use the reduced trace operation to get the density matrix of the subsystems. And if they are not equal to each other, if this particular inequality holds, then they are said to be correlated. And entanglement, which we generally think of, is maximal correlation, or we call it maximally entangled states. So this formalism I have discussed previously also in my videos. So for now we will take it for granted that this reduced tracing operation really exists. And now with this we move on to a bit of understanding of what is called maximally entangled state, and particularly throughout the entire discussion on Bell inequalities, this state, which will be called a singlet state, a singlet Bell state, will play an important role, and this will be the only entangled state we will be discussing. So this is a Bell state. This is a Bell state. There are 4 Bell states. This is one of those. And what this means is that you can try writing the density matrix of this state. It is a pure state, so the density matrix is just this, and trace out the B component. You will see that we will get identity by 2. So this is a maximally mixed state. Maximally mixed state. So what this means is that there is no information in this state about row A. You can't get any useful information of row A or row B. You can find row B also by tracing the A part. So this is what we call as maximally entangled states, because row AB, which will be this particular thing where psi is this, can't be factored into this, which is exactly identity by 4 in a Hilbert space of dimension 4. So this is what we call maximally mixed state, and particularly this is a singlet state. That means this has the spin 0. This is a spin 0 state. What it precisely means is that the total spin Z operator, spin Y operator, and X operator, the total operator. So the total operator is the the total operator, we know that suppose sigma I total, it will just be sigma I tensor identity. So this is A part, this is B part, plus I on A, which is identity on the A part, sigma I on B. So this is what we call the total operator, and this is the operator that acts on the entire wave function of the joint Hilbert space of particle A, particle B. I can call it particle 1, particle 2, doesn't matter. And this state, which is an entangled state, has a property that the sigma Z operator, Y operator, and X operator gives us 0. This can easily be proved because we can, suppose if we want to prove this one, we can write sigma X total in this form here. Because the S operator, the spin operator up to a multiple, is just the Pauli matrix, and then we plug in our state, the entangled state, and now we use the properties of these Pauli matrices. Particularly the sigma X Pauli matrix is a bit flip operator, the sigma Z matrix is a phase flipper, and the sigma Y is a bit phase flip. So what we will do is we will simply plug it here, and then we will perform sigma X on the first state to get 1, perform sigma X here also on the first state to get 0, and then similarly we will act this is on the second state, it gives us 0, so here, and this acts on the second state, it gives us 1, and the entire result is 0. Similarly we can again check for all the other cases, and what this tells us is that this state is rotationally invariant. This is quite easy to understand because you see these Pauli operators or the spin operators, they are the operators that generate rotation over this larger space of H1 tensor H2, and this state is completely like invisible to these operators. So they are rotationally invariant. What this means is that if we suppose think about the Bloch sphere representation, and we want to write this state psi in some different basis. So this state that we have here, it is written in sigma Z basis. What it means is that 0 and 1 are the eigenvectors of this sigma Z operator. But we can also write it in sigma dot n basis. Sigma dot n basis, and the rotational invariance guarantees the fact that the shape or the form of this state remains same even if you perform the basis change. So here this n plus is the eigenvector with the positive eigenvalue plus 1, and n minus is the eigenvector with negative 1 eigenvalue for this operator, which is the sigma n operator. So, and we see the form remains same. We will use it many times in our understanding of Bell inequalities. And also further we observe one more important property or important proof, that is, as I said, this is rotationally invariant. So that is what I have written here. This is sigma, total sigma operator about an axis B. And you can use the property of linearity of this tensor product to pull this B out, and this will be 0. And then what we can do is we can multiply with sigma dot A tensor identity on both sides, sigma dot A tensor identity from the left side, and then we see it will hit this part as well as hit this part, and then we can again multiply with a bra from the left side and squeeze the entire operator and take this plus sign here, it will become minus to get this particular part, and we get this equality here. But here this equality can easily be derived, because you see on the first part, because we have multiplied with sigma A tensor identity, on the first part this entire thing is an operator on the A Hilbert space, and this is the expectation value of this operator for this larger state, but the operator is on the A Hilbert space. What this means is that it is simply the operator expectation value in the reduced state space, and then that simply gives us this particular equality. And then here we see that it is like an expectation value of sigma A tensor sigma B, and this tracing out can easily be performed, because this reduced matrix, as this singlet state is a maximally mixed state, it is simply I by 2, and it will come out as identity, and there will have trace of O. But OA is simply this particular operator, and we have used here the summation notion, that there is summing over the repeated index I and j, over these repeated index I and j, and then we use the further fact that trace sigma I sigma j is 2 times delta ij, to see that it is just the dot product. So what this last point is telling us is that the expectation value of this particular operator is negative of the dot product of the axis over which you have chosen this. You see, this is a sigma, this is a spin operator over an axis A, this is over axis B, and its expectation value is just A dot B with a minus sign, but it is only true for this state particularly. So this also we will need further in the proof of this Bell inequality. So that's all for this video. It was just an introduction, and I will be making 3 to 4 of these videos. So that's all.